How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at the kinetic molecular theory of gases and the root mean square speed, or the RMS speed. So our objectives will be to describe the features of the kinetic molecular theory and how they explain the behavior of gases, as well as describe the significance of the root mean square speed and how it is affected by temperature. All right, so laws versus theories. Let's take a step back and talk about what the difference is between a scientific law and a scientific theory. Laws describe how things behave. That's all they do, right? So Newton's law of universal gravitation is that force equals some gravitational constant times the mass of object 1 times the mass of object 2 divided by the radius squared, right? So the law is describing what the gravitational force is. Put into words, every particle attracts every other particle in the universe with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. It's basically just saying, hey, we look at all these objects and this is what we see. We're describing how things behave. What a scientific theory does is it tries to explain why they behave that way. So this is what we see. Theories will explain why. So that's where the general theory of relativity comes in. Gravity is not a force, but a consequence of masses moving along geodesic lines in a curved space-time caused by the uneven distribution of mass. So laws describe how things behave. Theories explain why they behave that way. So we have PV equals nRT. That's our ideal gas law. That's how ideal gases behave, right? So the kinetic molecular theory of gases is going to try to explain why they behave that way. So first major feature is gas particles move in random motion. So they're moving all around in random motion until they bump into something, and then they change direction and they keep moving like that. All right. They also have negligible volume. So the gas particles themselves are really small compared to the volume of the container. So we just say that they have no volume. They also have negligible forces of attraction or repulsion. So are they attracted to each other? Ideal gases? No. Are they repelled by each other? Ideal gases? No. We're saying there's no intermolecular forces there. Constant average kinetic energy means that energy is transferred during collisions but is not lost. So these particles have energy. They can transfer it, but you're never losing the energy. So you have this gas particle moving along, bumps into another one. It can transfer that energy, but there's never going to be a loss. All right, average kinetic energy is proportional to the absolute temperature. So here you see I have some particles at 10 Kelvin. I have another particle at 20 Kelvin. Particles with the same temperature will have the same average kinetic energy. And you can see they're moving at the same speed because they're at the same temperature. Whereas the 20 Kelvin one is moving twice as fast. All right. Pressure is due to collisions. So you can see these gas particles moving around, bumping into the walls of that container. As temperature goes up, the average kinetic energy also goes up. So add some energy to it, things are moving around more, which means the particle speeds increases, they're moving faster, which means they're going to collide with the walls of the container more often, and they're also going to collide with more momentum, which means that the pressure will go up. All right. Gas particles that are at the same temperature have the same average kinetic energy regardless of the identity. So it doesn't matter if I got this H2 molecule bouncing around or the O2 molecule bouncing around. If they have the same temperature, they have the same average kinetic energy. That doesn't mean they have the same speed though. You know, heavier means they're going slower at the same temperature or energy. You know, if I put X amount of energy into a golf ball throwing it and I put the same amount of energy into a bowling ball, the golf ball is going to move a lot quicker, right? Because it's lighter. Not all molecules are moving at the same speed or have the same energy. So if here I got a mixture of gas particles, you can see some of them are going pretty slow, but some of them are also going really fast. And then most of them are going near the average speed, right? So graphically, looks something like this. We got fractions of molecules on the Y, and we have the speed in meters per second on the X. So you can see most of the particles are going about the average speed. So as temperature increases, more molecules are moving faster. So if I took the same sample and I heated it up, you would see the shape of it is going to start to change. You're going to see that there's more particles at higher speeds than there were before. All right, so let's talk about some different speeds. We got UMP, or the most probable speed. That's simply the high point on that curve. That is the most likely speed. If you look, it's got the highest fraction, it's highest up. So it's saying, you know, if you were to pick one at random, this is the most probable speed you would pick. The average speed is a little different, you know? And then we have the root mean square speed, which is even different. And I'm going to get into what's the difference between these two things. So the root mean square speed is the speed of a molecule that has the average kinetic energy. And that's not the same as a particle that has the average speed. So as temperature increases, what happens to these values? They all increase. The most probable speed increases. You can see it kind of shifted from here to there. The average speed is also going to shift and increase, and the root mean square speed is also going to increase as well. So average speed versus root mean square speed. Long story short, so they're not the same thing. The average speed is simply you just take the speed of all the particles, add them together, and divide by how many particles are there. Straight average, right? But the root mean square speed is, well, what if we took a molecule that had the average kinetic energy? How fast would it be going? Long story long. How are they not the same? Well, we know temperature is a measure of average kinetic energy. It's not a measure of average speed. So we're more interested in how fast molecules are going with average energy, not average speed. So average energy, let's say I had some particles. I had 4 particles with speeds of 12, 16, 18, 24. If I want the average speed, I just add them together, divide by 4. I got my average speed of 17.5. Now the root mean square speed is different. We got to figure out what is the average kinetic energy first. So we know kinetic energy is 1/2 mass times the speed squared. So if I do that with all the speeds for the particles, and I figure out the kinetic energy for each of those particles, and I add them all together and divide by 4, I get an average kinetic energy. And I go, all right, well, how fast would something be going if it had this average energy? And you get a slightly different number. You get 18 instead of 17.5. So long story long, they're not the same. Why do we care? You know, one's 17.5 and the other's 18. Why do we care? It's going to come up in future topics, you know, such as how much faster will H2 gas effuse out than O2 gas. So when we're talking about how quickly things will effuse or diffuse, we're more interested in the speed with average energy than we are the average speed. All right. So applications of kinetic molecular theory to gas laws. As we increase a volume at constant temperature, we're going to cause the pressure to go down. So here I got a container with a gas particle. It's moving around, it's colliding, causing pressure. If I increase that volume with the same temperature, moving at the same speed, what happens? Well, the average kinetic energy is the same, so the speeds are the same. The longer the distance, the more time in between collisions, which means there's going to be less pressure because the collisions aren't happening as often. So less frequent collisions means less pressure. Right? This explains Boyle's law. How come when we increase the volume, the pressure decreases? Right? That's Boyle's law. More applications. As the temperature increases at a constant volume, it increases the pressure. So we have low temperature, things moving slowly on the left. We got high temperature, things moving a lot quicker on the right. Why do we end up with higher pressure under higher temperatures? Well, if we have higher temperature, it means we got greater average kinetic energy, which means those particles are moving faster, which means they're going to collide more frequently, and those collisions have more energy. So we end up with an increase in pressure. And this is Gay-Lussac's law, right? We know that as we increase the temperature, the pressure has to go up as well. So summarize, can you describe the features of kinetic molecular theory and how they explain the behavior of gases? And can you describe the significance of the root mean square speed and how it's affected by temperature? And that's it. I hope you found it helpful. See you in class. Okay, bye.